L70 is bringing back in an idea that we learned back in chapter 4, a titration, where a titration is a commonly used to determine the amount of acid or base in a solution, and we've done titrations before. This process involves a solution of known concentration, which we call the titrant, delivered from a burette into the unknown solution until the substance being analyzed is just consumed. We can come up with a graph with our data of the change in the pH if we used a pH meter by adding the base. So the stoichiometric point, or which sometimes we call this equivalence point, is often signaled by the color change of an indicator. The process of an acid-base titration is often monitored by plotting the pH versus the amount of titrant added. This plot we call a pH curve or a titration curve. And so if you notice, the equivalence point is the point where the color change happens. Or that's the point where the number of moles of the acid and the base are at equivalent. They're equal. If we had a strong acid, strong base titration, we would use the formula or the equation to make water as our way of figuring that out, where we have H plus OH to yield to water. To compute the concentration of the H plus during the titration, we have to determine the amount of H plus that remains at the point and then divide by the total volume of the solution. We are going to do this, but sometimes our numbers can be very small. And so we have what's called a millimole, which we'll signify by MMOL. That helps us to have our numbers a little bit easier to work with. Okay, so it's 1/1000th of a mole is the size of a millimole. But it's nice because normally we think of molarity equals moles over liters. Well, if we're using millimoles, the molarity is equal to the millimoles divided by the milliliters of the solution. And so that will help us when we're having very small numbers to solve. So we are going to determine in example 7, 3 different points during a titration. So hydrogen cyanide gas, HCN, is a very weak acid, which the Ka is given, when dissolved in water. If a 50 milliliter sample of the 0.1 molar HCN is titrated with 0.1 molar sodium hydroxide, calculate the pH of the solution at these 3 points. Alright, so we're going to do A first. When 8 milliliters of the 0.1 molar sodium hydroxide has been added. Okay, so we have our hydrocyanic acid, the HCN, and we are adding the sodium hydroxide to it. But the sodium is a spectator ion. It's not going to have an effect. So we're just going to leave that off, and instead we're going to have the acid plus the base. Okay? And so by doing that, we can then kick out the H, or take away the H from the acid, it donates, and we make cyanide plus water. So we have to do the stoichiometry next. We know that for the acid, we have 50 milliliters of 0.1 molar solution. So to find out how many millimoles are there, we can take our 50 milliliters times the concentration, the 0.1, and that will give us that we have 5 millimoles of the acid to start. Okay, and we are adding in 8 milliliters of 0.1 molar sodium hydroxide. So if we take our 8 milliliters times our 0.1 molar for the hydroxide, we get that is 0.8 millimoles. We are starting with 0 of the cyanide millimoles, and water is a liquid, so we're not concerned. So this is what is before the reaction taking place. So now we need to subtract and gain on the product side, so we're going to subtract 0.8 millimoles from both reactants and add it to the product. So after the reaction takes place, we now have 4.2 millimoles of our acid left. We have 0 millimoles of our hydroxide left because we used it all up. And we now have 0.8 millimoles of the cyanide present in our solution. Okay, well, to use this stoichiometric part into our solving out for the pH, we need to go back to molarity. And to find the molarity, you have to take millimoles divided by the total volume in milliliters. Well, the total volume of the solution is equal to the amounts of liquid added. So we had a 50 milliliter sample of the acid, and we added 8 milliliters of the base. So our total solution volume is 58 milliliters. Okay, so we need to divide our millimoles divided by the 58 milliliters to get a molarity again. So for the acid, our molarity now is 7.2 times 10 to the negative second. And for the cyanide, it is now 1.4 times 10 to the negative second molar. Okay, so we can use these two numbers now in an equilibrium expression. So we are going to now break down our acid into the proton plus the anion. And so we are starting with, and the reason why we're doing this is because we need to solve for the H plus so that we can know our pH. We are starting with the molarity that we just solved for both spots. So the 7.2 times 10 to the negative 2 is our initial for the acid, and 1.4 times 10 to the negative 2 is our initial for the base, or the conjugate base. So after our change at equilibrium, we have the 7.2 times 10 to the negative 2 minus x, 0, or excuse me, x, and then 1.4 times 10 to the negative 2 plus x. So now we get to plug into an K expression for this, and it's products over reactants. Our Ka given is 6.2 times 10 to the negative 10, and so that's equal to our x, we're going to assume, times 1.4 times 10 to the negative 2, all over 7.2 times 10 to the negative 2. So x is equal to 3.3 times 10 to the negative 9 molar, and that is our H plus. So plugging into the pH equation to know our pH at this point, negative log of our H plus, the 3.3 times 10 to the negative 9, our pH at this point in time during the titration is 8.49. So that is on the basic side. Okay, well, let's do for B now, at the halfway point. So at the halfway point of the titration, our halfway will be when we have half of the total moles of the HCN originally present added from the hydroxide. So originally present, so the amount, this is B by the way, the amount of the acid originally present is equal to our volume times the concentration that we were originally given, the 50 milliliters times the 0.1, and that is equal to our 5 millimoles, like we had before. Okay, so the halfway point is when the hydroxide ion moles are equal to the half of what we originally have for the HCN. So half of that would be the 2.5 millimoles. Because half of 5 is 2.5. Okay, and so then now, if we know that it's a 0.1 molar solution and we are adding 2.5 millimoles, then we just need to know our milliliters. And so doing a little cross multiplication, we can find out that we need to add 25 milliliters of the NaOH to reach this halfway point. Okay? When the concentration of our acid is equal to the concentration of the conjugate base at the halfway point, this is what's going to happen. Then we learned before that the pH can equal to the pKa. Okay? So we don't need to do anything with an acid expression right now. We can just plug in where if we know Ka is the 6.2 times 10 to the negative 10, then we could take it like we would if it was H plus and take the negative log of that to find our pH, because we're solving for pKa there. So the pH at the halfway point is 9.21. So that has increased from after part A. And so the halfway point is when half of the moles of the acid originally present are added with the base, and then you can solve for the pH there. So then for C, we want to solve for the equivalence point. This is when the moles are equal to each other. Okay, so if we originally had, and I'm just rewriting this because I have to go to a new page each time, we had 5 millimoles of the acid added originally. That means that at the equivalence point, we also have 5 millimoles of our sodium hydroxide added, because the moles of the base have to equal the moles of the acid at the equivalence point. Okay, so then to figure out how many milliliters of the sodium hydroxide were added, we can figure out using our 0.1 molar is equal to our 5 millimoles over the milliliters, cross multiply, and you get that 50 milliliters of the sodium hydroxide was added in order to reach this equivalence point. Okay, so at this equivalence point, if we need to know the pH, we know that the conjugate base has taken over. So we are going to use the base equation this time, where we use our Cn, which is our conjugate base, and plus water yields the acid plus OH. And by doing this, then we can find the OH concentration, which will help us find the pH. Okay? So we need to know the concentration of our Cn at the equivalence point. Well, if we have our 5 millimoles originally added of the acid divided by the total volume. So we had 15 milliliters of our NaOH added, and we originally added 50 milliliters of the HCN. So our total volume now is going to be 100 milliliters. So that is equal to 0.05 molar. Water doesn't matter. We have zeros for the other two. Now, so at the equivalent, or at equilibrium, we have the 0.05 minus x and x and x. So before we go further, we need to switch our Ka to Kb, because we did the Kb expression, or equation, the base equation. So to switch it, divide by Kw divided by the Ka. So the Kb is 1.6 times 10 to the negative 5. So now, with our K expression, we'll have the Kb equal to the product times product, so x squared over, and let's assume that the bottom will just be 0.05. So x here is equal to 8.9 times 10 to the negative 4 molar, which this time is the OH concentration. So now that we know the OH, we can solve for the POH by taking the negative log of that and the POH I got to be 3.05. So then for the pH, we have to subtract that from 14, and the pH is 10.95. So at the equivalence point, the pH will be 10.95. So we can do these calculations for any point on our titration curve when we have a titration of a weak acid with a strong base. A couple of things to think about with our pH curve and titration curves is that the strength of a weak acid has a significant effect on the shape. So a strong acid, if you notice the red line is the strong acid, and it starts off really low in pH, and then it has a very steep point which it switches over to being in the base side of things. But a weak acid starts off higher and it's more gradual, a little bit more gradual. So the weaker the acid, the greater the pH value at the equivalence point as well. Because if you notice on this graph, the equivalence point of the strong acid, the equivalence point is when it's at a slope of 0. So the equivalence point for the strong acid would be about here. Whereas if we're following the blue line for the weak, the equivalence point would be somewhere up there more. So the pH value for strong is going to be higher than if it was weak strong. The vertical region that surrounds the equivalence point becomes shorter as the acid titrated becomes weaker. So if you look in this picture, it's kind of shaded in darker where these equivalence points are. And if they're all going to the same pH at the end, then it gets shorter and shorter, that vertical area where the pH changes. So we are now going to solve instead if we have to solve for the Ka. So a chemist has synthesized a monoprotic weak acid and wants to determine its Ka value. To do so, she dissolves 2 millimoles of the solid acid in 100 milliliters of water and titrates the resulting solution with 0.05 molar sodium hydroxide. After 20 milliliters sodium hydroxide that has been added, the pH is 6. So what is the Ka for the acid? Well, we don't know what our acid is, so I'm just going to use HA, and we're adding it to sodium hydroxide, which is sodium, has no effect. So we'll form water, and then the conjugate base. Okay, let's do the stoichiometry first. So if we have 2 millimoles being added first of the solid acid to the sodium hydroxide, and we know the molarity and how much sodium hydroxide is added, so we need to figure out the millimoles of that. So 20 milliliters times our concentration, the 0.05, will give us that we have 1 millimole of our sodium hydroxide. We have nothing to do with water, and we have 0 to start for the conjugate base. So we are going to use up our base. So we're going to subtract 1 from the reactants and add 1 millimole to the product side. So after the base has been used up, we have 1 millimole of our acid left, 0 left for the base, and 1 millimole for the conjugate base. Okay, well, before we can go further, we need to convert this to molarity again. So we need to divide by the total volume, which the total volume this time, our total for the solution, is equal to, we have 100 milliliters of water plus 20 milliliters of the acid, or of the base. So that's 120 altogether. So when you divide, the acid now has a molarity of 8.3 times 10 to the negative 3, and the conjugate base has the same thing, 8.3 times 10 to the negative 3. Alright, so now we can do a Ka expression using this bit of information. So again, we don't know the acid, so we're just going to use the generic acid equation, and we can use our molarities we just saw for those two. After equilibrium, we'll subtract X from the reactant side and add X to the product side. So now we can set up a Ka expression because we want to solve for the Ka. We need to know the value of the Ka. So the Ka is equal to products of reactants. So we have, we can assume here, the 8 point. Well, to know what X is so that we can solve for our Ka, X is the concentration of the H plus at this value, at this point. And if we are given that the pH is equal to 6, we can solve for the H plus concentration by taking the anti-log. So 10 to the negative 6 means that the H plus is equal to 1.0 times 10 to the negative 6 molar. So we can plug that in for X. And guess what? The 8.3 times 10 to the negative 3 cancels out. So our Ka is equal to the H plus concentration, which is 1.0 times 10 to the negative 6. And this is because the sodium hydroxide was actually added at the halfway point. So we are able to use this bit of information. Last but not least, titrating a weak base with a strong acid can be treated using our same procedures from our previous conditions. But always think about the major species and then decide whether a reaction occurs that runs essentially to completion. In all of our cases so far, they had. If this does occur, let it run to completion and do the stoichiometric calculations like we did, and then choose the dominant equilibrium to calculate the pH. There are a lot more case study examples on how to do this kind of how to do these problems in your textbook between pages 728 and 742. But I thought this video was long enough, so I decided not to include them. So problems this time are numbers 12, 55, 59, A through C, and 67.